working. I'd like to thank the organizers for inviting me to this very nice conference. This is my first time at String Math, and I had previously assumed that it's just a slightly more mathematical version of strings, but it's a little different from what I expected. It's a lot more mathematical. And unlike my some of the previous physicists' talks, in which they very nicely distilled beautiful mathematical results from their work in a way that is appealing to mathematicians, I will adopt a somewhat different approach. I will present questions that I find interesting from a physicist's perspective. I will describe some of the clumsy methods we invented to address these questions. I'll tell you some results, a lot of which are numerical, which will be distasteful to mathematicians, but however, they do sometimes lead to exact conjectures, which mathematicians may like to prove, and eventually, hopefully, some mathematicians will help us develop more powerful tools to address these questions that we're interested in. So I'm going to discuss works with these list of collaborators over the last couple of years. Here's the outline of the talk. I'll describe some motivations and the questions that I find interesting, and I'll describe various constraints from modular and crossing, and I'll comment on superconformal theories, and finally discuss some use of modular constraints from genus 2. Okay, so to begin with, let me clarify what I mean by 2D conformal field theory, because different people, both physicists and mathematicians, might mean slightly different things when they speak of a 2D conformal field theory. They are sometimes one relax or omit some of the axioms. I'm going to take what I consider to be sort of physically the strongest and most reasonable definition of a 2D conformal field theory. I'm going to demand, first of all, this is going to be a quantum field theory. There's a local conserved stress energy tensor traceless that give rise to Virasoro symmetry, holomorphic and anti-holomorphic, with some central charge C. For most of the talk, I'll assume the holomorphic and anti-holomorphic part have the same central charge, but it's not really necessary for much of the discussion. Importantly, there are local operators that organize into unitary representation. Well, if it's a unitary conformal field theory, they're organized into unitary representations of the Virasoro algebra, both on the holomorphic and anti-holomorphic side. There's going to be an associative operator product expansion. And importantly, I'm going to insist on having modular invariance, which in fact, it suffices to have modular covariance of towards one-point function that will ensure modular invariance of the full conformal field theory. As a disclaimer, I will not address non-local operators and boundary states. Those are interesting, but it will be not part of this talk. Okay, so let me first discuss some of the known knowns of 2D CFTs. That is, theories that we know that do exist with properties that are known or exactly solvable. There are compact and rational conformal field theories described by, for example, a large class of these described by coset models. There are compact and irrational conformal field theories like free orbifolds and or Calabi-Yau models, supersymmetric, that we know some things about. There are non-compact and irrational conformal field theory that are exactly solvable, like Liouville and Toda theories, and non-compact coset models, such as the cigar CFT. Now, for the rational CFTs, there are a lot of tools that have been developed to address these theories. These are textbook material. So, for instance, there are a lot of known analytic constraints on the spectrum because they organize into finite-dimensional modular representation in terms of their characters, and then the fusion rules is also relatively well understood. And we know a large class of examples of nice 2D CFTs are constructed as superconformal theories. And for these, much is known about the supersymmetric sector, and their modular space of exactly marginal deformation, which I refer to as the conformal manifold. But there's not actually that much known beyond the BPS sector of the theory. And I'll mention some results very briefly on this. Now there are the known unknowns. That is, the theories that we know exist and we love, but they are results I would love to know about these theories. That would like to know their spectrum, but these appear to be somewhat beyond the reach of current technology. And For example, in superconformal theories beyond the BPS sector, such as Landau-Kinzigman models or Calabi-Yau models, or symmetric product orbifolds of say T4, K3. And now these superconformal theories come with a rich conformal manifold. You can deform the theory by exacting marginal deformation. There are some points in modular space where theory is exactly solvable, but very often the physically interesting theories lie somewhere else where the theory is genuinely strongly coupled. And now, in principle, one can start with a solvable point on the conformal manifold and probe elsewhere using conformal perturbation theory, and they typically have non-zero rates of convergence, unlike the ordinary perturbation theory starting from free theory, free quantum field theory. However, these are technically very difficult to do, and so far, not too much useful results have been obtained in this way, because it's hard to carry on conformal perturbation theory to high orders. This is important for application to ADS3 CFT correspondence. One classic example of this is the D1, D5 CFT. These are also important for perturbative vacuole string theory, of course, in order to figure out a non-BPS string spectrum and say a Calabi-Yau modification in a quantum regime. And there are also potentially interesting, potentially irrational compact CFTs, which can be possibly realized as IR fixed points of some controlled but non-supersymmetric RG flows. An example, which is not particularly well known, is coupled Potts model. So for these kind of theories, there was no very useful direct, exact CFT technique to address. And then an interesting class of non-unitary conformal field theories are non-unitary conformal supergroup sigma models. These play an important role for strings, perturbative string theory in ADS. And in fact, there has been a lot of effort by people here, Volker Schamerus and collaborators, on the subject. But a lot of interesting questions are still not known about these CFTs, despite that they have a lot of symmetries. OK, so now I'm coming to the unknown unknowns. These are questions about the theories that we don't really know if they exist. But it'd be interesting if they do, and it'd be interesting question we'd like to ask. Even for rational conformal field theories, we're very, very far from classifying rational conformal field theories. As an example, even the simplest, one could argue the simplest notion of rational conformal field theories is an extremo meromorphic CFT. That is, you just have a single modular invariant holomorphic vertex algebra with central charge that's a multiple of 24. And apart from the famous monster theory, in the case of C equals 24, we don't really know if they even exist beyond that. Now, there has been, that's not due to the lack of effort, there has been a lot of effort to try to construct and rule out such theories, but so far it's still inconclusive. The second question is, I emphasize the modular invariance because, well, I'll come back to more about to say more about this in a moment. But one can ask the question, what value of central charge when the central charge C is greater than 1, and well, if C is, let's say, less than 1, the unitary ones are classified as minimal models. If C is greater than 1, one can ask what value of central charge can be realized by compact unitary CFTs. And by compact, I mean the nicest kind of CFTs with discrete spectrum, SL2 invariant vacuum state, and so forth. And a different way to phrase the same question is, can a unitary Virasoro algebra, which is a perfectly consistent vertex algebra that has associative OB, can it always be embedded in a compact modular invariant theory? And that's far from obvious. For example, if I ask, is there CFT, compact unitary CFT with central charge C equals 1.1? It's not known, at least not to me. Now, the twist of operator is, or primary operator of Virasoro algebra, defined to be the difference between dimension and spin. So if the twist is 0, the operator corresponds to conserved currents, which correspond generally to higher spin symmetry. It turns out that, actually, if you go through the list of all the compact unitary 2D CFTs that you can think of, that you can establish the exact spectrum, they appear to always have 0 twist gap. which is somewhat strange. So you might wonder whether that's always true. It turns out that one can prove, without too much effort based on modular invariance, that there's an upper bound on the twist gap in the spectrum of versorial primaries, which is C minus 1 divided by 12. Now, for non-compact theory, that is saturated by Liouville theory. But for compact, there's no example that even has a non-zero twist gap, as far as I know. So that's also somewhat surprising, because it means that either we're missing, most of the compact unitary irrational conformal field theory, just don't know how to construct them, or there's some very strong constraint that we just have no idea how to prove. And are there really compact conformal field theories of large central charge and large gap in the spectrum of versorial primaries? This is, via holographic correspondence, is really equivalent to asking a question: does something like a pure quantum gravity in ADS3, three-dimensional entity series space, does it really exist? And by pure quantum gravity, I just mean any theory of quantum gravity with a mass gap of Planck scale. Now, I should say that this is something that's often taken for granted for people that try to address puzzles about black holes from holography using CFT and the bulk reconstruction. But recently, some prominent people put this to doubt. Some people believe that maybe these theories don't exist. And finally, a general theme is the kind of thing we do is, to what extent does the low-lying operator spectrum of a conformal field theory pin down the entire theory? I mean, in some sense, this is what really physics is about. We measure a field constants and want to figure out what the theory is. And again, from the holographic point of view, this is a kind of question about the existence and uniqueness of ultraviolet completion of gravity plus matter system in entity series space, in this case, in 3D entity series space. OK, so these are some general questions. Now let me get down to the actual details. So beyond in the standard textbook technique beyond rational conformal field theory is fairly limited. For instance, conformal perturbation theory, when it's available, is hard, as I already mentioned. The old 2D conformal bootstrap approach was aimed to construct exact solutions, and that was extremely successful in solving large class of rational theories. But we like to understand irrational theories, and the new conformal bootstrap, a reboot of the conformal bootstrap program, started with this groundbreaking paper 9 years ago by Rotazzi, Richkov, Tony, and Vici. And the aim was, in fact, slightly less ambitious to begin with. We just want to rule out possible theories. By that, I mean to rule out possible spectrum, possible structure candidate structure constants, and kind of carve out the landscape of possible theories. So our goal here is to carve out the space of 2D unitary CFTs. I'm not going to achieve that goal today, but that's the motivation. We'd like to know, for example, what are the possible spectral local operators and structure constants in the unitary 2D conformal field theory? And much of this game relies on whether one can ask the right question and put the right assumptions on the theory to get interesting constraints. OK, so just to be slightly more concrete now with some pictures, the conformal bootstrap essentially amounts to imposing on the given set of local operators with operator product expansion, we'd like to impose crossing invariance of the 4-point function on the sphere, which is equivalent to the associativity of the operator product expansion. And modular invariance, which, as I said, is entirely captured by the modular covariance of torus 1-point function. Now, the associativity of OPE is a property we'd like to demand on conformal field theory in any space-time dimension, which is what's often done. Modular invariance, the way I phrased it, is only understood in 2D. It will be very interesting to figure out what the analog of this in higher dimension is, but so far the proper analog is not understood in higher than 2 dimensions. I should emphasize that the modular invariance is important for many reasons, but in particular, let's say if you have a consistent conformal field theory in 2 dimensions, it happens to have a discrete global symmetry, you can restrict yourself to local operators that are invariant under that global symmetry. And that, of course, will produce a sub-vertex algebra that is consistent in the sense of OBE, but it will violate modular invariance. So to impose a modular invariance, really, allows you to address whether you have a complete conformal field theory. And let me begin with a simple example. Let's study the modular invariance of the torus partition function. So this is a partition function of the modulus tau and tau bar of a torus. Okay, and C and C tilde here are the left-hand holomorphic, anti-holomorphic central charge. L0 and L0 bar, the Virasoro generators, and the holomorphic and the anti-holomorphic side, and trace is over the trace of the Hilbert space of the CFD on the circle. The Hilbert space of CFD on the circle is mapped to the Hilbert space of local operators. To demand that this is invariant under tau goes to tau plus 1, one of the generators of the modular group is just equivalent to the requirement that all the local operators have integer spins. That's not a big deal. By the way, if you are dealing with, say, fermionic theories, according to my definition, I would like to insist on applying GSO projection to make the theory actually fully modular invariant. Now, the invariance under tau goes to minus 1 over tau, the other generator of the modular group, is much more non-trivial and constrains the operator spectrum in a very non-trivial way. For example, as was famously shown by Cardy back in the 80s, the modular invariance relates the growth of the number of operators at high scaling dimension to the operator content at very low scaling dimension. But in fact, it goes much further. It was recognized in 2009 by Simeon Hillerman that the modular invariance not just controls the growth of operators at very large dimensions, but actually can be used to constrain low-lying operators as well. You might say that, well, here I have some non-holomorphic, well, it is just some general function. If it's modular invariant, you can take some smooth function on the fundamental domain of PSL2Z. Why is it a big deal? The thing that makes it a big deal is that it emits an expansion Q and Q bar with positive integer coefficients, and that makes all the difference. So this work of Hillerman was subsequently refined and optimized. Took a while to figure out really how to do that. So let me describe how that's done. To begin with, we'll organize, because as I said, we'll organize the spectrum of the local operators into representations of the Virasoro algebra. The torus partition function will be written as a sum over Virasoro characters, holomorphic and anti-holomorphic, with some coefficients that are degeneracy of primaries of some weight h and h tilde on the holomorphic and anti-holomorphic side. These coefficients are positive integers. By the way, just for simplicity notation, I'm going to assume c greater than 1, and apart from the vacuum character with h equals 0, all the others are non-degenerate. I'm just going to impose not even the integerness condition on the coefficients, but just that they're positive. And that z is modular invariant, and see what we can say about this. And I'll also impose that the spin of the primaries are integers, as required by modular invariance. So we aim, the rule of this game is that we like to rule out some set of spectra with some hypothetical properties. By analyzing this modular invariance condition, which I wrote as the modular crossing equation. So I'm just saying the z, I'm just rewriting this in terms of the sum of characters. Okay, and our strategy is the following. So we want to implement the constraint that these coefficients d are positive. So the spectrum of the theory obeys such a modular crossing equation with some positive coefficients d. So the strategy is that we're going to turn this kind of functional equation into a set of linear equations by applying a linear functional, a very simple one, to this, which this is nothing but taking some derivative in tau and tau bar at the crossing invariant point, tau equals I. And so for some spectrum I, which so all the operators, the weight of the operators sit in this spectral set, and would like to seek a linear function of alpha such that under whatever assumption you put on I, alpha acting on this function takes a value that is positive. You may or may not be able to find such a linear function of alpha, but of course, if you do find alpha, you immediately rule out the possibility of such a spectrum, because then you plug this into you apply alpha to this equation, you get a contradiction, because the left-hand side is positive, the right-hand side is 0. Okay. This very simple idea appears to be quite powerful, in fact. And just to give you an example, one type of hypothesis you can make on the spectrum is the gap in the scaling dimensions. That is, you always have a vacuum state, which is correspond to identity operator that has dimension 0, and maybe there's a gap called delta 0 above that. So if you plot the dimension delta, this is the sum of the left and the right holomorphic, anti-holomorphic weight, and the spin, which is the difference between the holomorphic and anti-holomorphic weight. These gray regions are excluded by unitarity bound, so these are not allowed in unitary conformal field theory. And assuming a gap just means that I have let's say, a vacuum state, identity operator here, and then I exclude this region over here. But above that, anything is allowed. Okay? Now, in practice, we do this. Well, in practice, you can take some linear function, of the form I wrote before. You can take, just a few derivatives and see if you can rule out some possible gap, and the answer is you can. But of course, the more complicated this linear function you allow it to be, the stronger result you might be able to obtain. And in practice, in order to optimize these bounds, we have to resort to numerics because these would involve higher and higher derivative order. And in practice, we need to truncate on the range of spin, and one has to carefully ensure numerical stability. There's some standard computer package designed by David Simmons-Duffin for this kind of purpose. This was originally designed to analyze the crossing invariance of a full-point function. It's the same thing that can be applied to this modular case. I'll just tell you some results. OK, so here's a plot. So this horizontal axis, the central charge, starts from 1 and goes up. And the vertical axis is the gap in the spectrum of various order primaries. And I would like to put an upper bound on that gap. So basically, for given central charge, there'll be some value above which, if the gap is bigger than that, it will be inconsistent with marginal variance, it turns out. And this is the result that's optimized in this paper last year. There are two curves here. OK, so above that is excluded. Let me say what these things are. So this blue curve here, which is actually a straight line here and then turns around a little bit, is a bound on the gap of all the various order primers that are not the vacuum. And the red is if you just want to bound the gap in the scalar primary. So this you can do. And by definition, this is going to be weaker than this. They coincide if it's less than 1, which is over here by unitarity bound. But otherwise, this is strictly weaker. So you have some interesting features like so. Well, one can obtain this numerically, but how do you know that these results are really optimized? Well, it turns out there are theories that saturate some of these bounds. For example, it turns out that for some special values of central charge, these bounds are saturated by WZW models at level 1 with symmetry group SU2, SU3, G2, SO8, and E8. Don't have too much of an explanation, but let me just point out this E8 case. It's kind of interesting because this bound happens to be equal to 2, and central charge is equal to 8. And that in particular implies that you have a unitary conformal field theory of central charge less than 8, there's always going to be a relevant deformation. EA level 1. It's just 8 free bosons at a special point in the modular space. OK. And I should say that this, again, only plotting up to like 23 or so, it turns out this red curve rises sharply and blows up at c equals 25. There's an explanation for why that's true. So the scalar bound only exists for c up to 25. The all-spin bound exists for arbitrary c. We don't actually know what it asymptotes to. So numerically, it looks like it's less than c over 9. I should say that numerically, it's become increasingly difficult for large c because this linear function that is required to optimize the bound involve higher and higher order derivatives, and you need that higher derivative orders when the central charge is large. So over here, you can do this on a laptop in like 20 minutes. Over here, you need a cluster and run it for a week. So it's I have to say, this semi-definite programming involved here is actually pretty simple because these Virasoro characters are very simple objects, unlike the actual conformal blocks. So, which I'll come to in a little bit later. This is really a problem of some flavor of harmonic analysis, and perhaps some mathematician can sit in their office in one afternoon and figure out the exact answer. But so far, we don't have that exact answer. I'm sorry? So there's no holomorphy here. So actually, in fact, it's not clear if these are cusps or. Yeah, this is EA level 1. Yeah. Not just from this, no. Okay. A conjecture, so as I said, the numerics suggested that this thing asymptotes to something that's less than C over 9, and a conjecture that it was would be motivated by thinking about 3D gravity suggests that perhaps this thing was asymptotic to C over 12 plus something that grows less than linear in C, but that's never been proven. Maybe someone can prove it, and even numerically it's hard to check that because we can't really go above C equals 200 or so. Okay. So that's a very simple example. Now let's turn to the analysis of operator product expansion. So we studied the sphere 4-point function of some primary operator. And so these can be decomposed into Virasoro conformal blocks for the sphere 4-point function with some OP coefficients. They're structure constants of the conformal field theory. And it's useful to think of this in terms of the pillow geometry, where you kind of do a conformal mapping to straighten out this sphere by you can stretch the 4 vertices and turn this into basically 2 parallelograms kind of glued along the edge. It's nothing but T2 mod Z2. In terms of that torus, the cross ratio of these 4 points is mapped to the modulus of torus in this way. This Q, which is e to the e to the pi I tau, is called the elliptic gnome. Now, this parameterization is nice for the following reason. So the cross ratio, which this 4-point function depends on, lives on a complex plane, and the coordinate function has singularity of 0, 1, and infinity. If you just naively, based on the usual definition of a conformal block, is written as an expansion in power series in Z, naively you will encounter singularity at 1, so the radius convergence would be 1. But in fact, it's analytic on the entire complex plane, away from the branch graph from 1 to infinity, and more. This is made manifest in the representation in terms of the Q parameter, this elliptic gnome. So it turns out this entire complex plane, Z-plane, is mapped to this I-shaped region on the Q disk. But in fact, the conformal block, as a function of Q, has unit radius convergence, or converges on the entire Q disk. So this allows you to actually continue beyond the branch cut to other sheets. There are infinitely many of them, infinitely many sheets. And it's very useful to work with the Q expansion rather than the Z expansion of the conformal block. This makes manifest various analyticity property and positivity properties, and also allows for very efficient numerical evaluation for the reason that e to the minus pi is a small number. So this was first observed by Zamolodchikov in '87, but this pillow was emphasized in this very nice recent paper from a couple years ago. So in fact, the practical numerical computations of the conformal block we do makes use of Zamolodchikov's recurrence relation, which is an efficient way to compute this Virasoro block as an expansion in this Q parameter. And that makes use of some of the analyticity property of the block when continued with back to center charge or with the back to weights. I'll mention a little bit of that later. Okay, so now let's discuss the crossing equation for the sphere 4-point function. It takes this form. In terms of the formula, it looks like this. So there's some conformal block summed with multiplied by structure constants, and then there's other cross-channel conformal block multiplied by another set of structure constants, and with a conformal cross ratio Z mapped to 1 minus Z. For simplicity, if you restrict to a pair of identical primaries, then you have this product of structure constants now becomes squares. And in a unitary conformal field theory, these are going to be, the C coefficients are real, so C squares are positive. So just like the previous modular crossing equation, you have some positivity property multiplied by some function. These functions are now pretty complicated, but okay, we can do numerics and run the same semi-definite programming and try to figure out constraints on these coefficients. Now, if you don't make any additional assumption at all, in this case, it turns out the constraints is rather weak. You have to be clever with assumptions you make. So, for example, if you want to bound the gap now of not just any operator in CFD, but the operators that appear in the specific operator product expansion for given external operators, you can try to do that, but you get a stronger bound if you assume, let's say, as an example, if you assume that there are only scalar Virasoro primaries. Now, this is a very, very special assumption, by far, far from the most general conformal field theory, but let's make such an assumption for the moment. Assume that there are only scalar Virasoro primaries, so running in the OP of a pair of, say, scalar primaries on the outside, and using crossing equation, one can bound the gap. It turns out it looks like this. So this region is excluded. So previously in the exclusion plot, the horizontal axis was the center of charge. Now the horizontal axis, now I'm fixing the center of charge, and the horizontal axis is the external operator dimension, and the vertical axis is the gap. So I'm excluding this region, and with better and better numerics, it kind of goes down to flat, basically. Now this was, in unpublished work, first was found by Bolt van Ries. We also found this later, not aware of his earlier work, but this was not published. We didn't publish this because you can do something better than just bounding the gap and OP coefficients for the first few operators. By the way, there's some interesting feature here, but I'm not going to say this for now due to lack of time. But let me explain something that you can do better with. Okay, so let's take this 4-point function with some two pairs of identical external operators. I'm going to define what I call a spectral function. It's the following very simple object. It's basically, I take the 4-point function, decompose as the sum over conformal blocks, and just truncate that sum to primaries up to some given dimension called delta star, and normalize this by the entire 4-point function. So this I call the spectral function. I evaluate this at the crossing invariant point, z equals a half. That's entirely for technical convenience. Now, this is some arbitrary definition. It's not terribly impressive. But I just want to note that if you know the spectral function as a function of delta star, you know the distribution of OP coefficients in a given operator product expansion. OK. Now, this is just a trivial definition. But the non-trivial thing is that we can actually bound the spectral function using crossing equation in a useful way from semi-definite programming. So the way that goes is the following. So the crossing equation I wrote down earlier, which involved the f of z and f of 1 minus z, if you take the derivative again at the crossing invariant point z equals a half, you do this with odd derivative order, you can turn that into a set of just linear equations on the c squares in this way. Now keep that in mind. Where, let me just emphasize again, this f upper mn refers to a derivative of the conformal block at the crossing invariant point, mth order with back to z, nth order with back to z bar. So here I always take m plus n to be odd, that's the crossing equation. The f0, 0, that's the conformal block itself, evaluate the crossing invariant point. So these are the odd ones, odd derivatives that appear in the crossing equation. These are the original conformal blocks. Let's consider this inequality where theta is a step function. So this takes value 1 for positive arguments and 0 for negative arguments. So this basically only keeps the stuff below this cutoff dimension delta star. And these y's are some real coefficients. It may or may not be possible to find y's such that this equation is these inequalities are simultaneously satisfied for all operators in the spectrum. By the spectrum here, I mean the spectrum that appear in the OPE. Now, if you can find a set of y's such that this equation is obeyed, with a big if, then if you take the equation, multiply by c delta squared, this OP coefficients, and sum over delta, then by the crossing equation, this third term, all the terms in the sum will drop out by the crossing equation. And the first two terms, the ratio of this with this is just the spectral function. So I get that the spectral function is greater than or equal to y0, 0. I should mention that this conformal block a value is equal to 1/2 is always a positive number. That can be proven. So in this way, so the point is that if I can find such coefficients, then that produces a lower bound on the spectral function as a function of delta star. So for each delta star, I do this once, I get a lower bound. For another value of delta star, I get another bound. Okay. And an optimal lower bound will be achieved by maximizing y0, 0 subject to this inequality. This is, again, a standard kind of problem that can be solved numerically with semi-definite programming. There's an opposite inequality you can do to get an upper bound. Okay. Well, that's nice, but are these bounds actually non-trivial? So now, again, let's assume for the moment that they're only scalar Virasoro primaries. And assume some charge is greater than 1. Let me say that this is, again, emphasize that this is very, very special. You can try to bound the spectral function from above and from below numerically. So we do this for a given central charge. If you pick a value of central charge, and you pick a value of external upper dimension, and you get, and this is a spectral function. It ranges from 0 to 1 by definition. It's supposed to be monotonic. And there's upper bound, and there's a lower bound. And as you improve the numerics, you get a stronger and stronger bounds by including more and more linear functionals. I should say that the bounds are a priori rigorous, just using linear functions up to some given derivative order, but you can optimize it by including more and more basis linear functionals. And they appear to converge to something, to nail down a window. These green to red curve, these are bounds. So they exclude the region up here, exclude the region down here. So kind of, it's moving towards pinning down the spectral function. And this black curve is Liouville theory. So now the Liouville theory happens to be the only known example of a conformal field theory with that property of the only scalar Virasoro primaries. But what this suggests is that, in fact, we conjecture that it's an only unitary conformal field theory with C greater than 1 that obeys crossing and only has scalar Virasoro primaries. So we can discuss a numerical convergence, but let me just first say a few things about the Liouville theory. Now, of course, so Liouville theory normally, traditionally, was defined by some action. You can try to formulate a path integral, but that's it's hard to calculate anything using that description. The picture is that there's some scalar field with some background charge and with some scalar exponential potential, and the states of the theory we're talking about the states of the theory on the circle, which are mapped to local operators in the CFT, are scattering states of some wave that bounce back in the field space. So the Virasoro primers, the Liouville theory as a CFT, are described by wave functions in the field space of this form of some scattering wave, where these exponents are related to Liouville momentum P, which is going to be a real number here. This is for C greater than 1. Now, by assuming analyticity in this momenta, this theory was solved by Dorn, Otto, and Zamolodchikov's. So we know the reflection coefficients exactly. We know the structure constants exactly. These are very non-trivial formula. This involves some Barnes double gamma functions, very non-trivial. And the crossing, the statement that this obey crossing was established by Teschner. Now, all these, incredibly impressive formula, we can get from numerics without assuming anything other than that there are only scalar Virasoro primaries and the theory is unitary. In fact, even unitarity can be dropped. It turns out that if you already assume, so earlier I showed you the plot that suggests that the upper and lower bounds will converge when you assume unitarity. If you assume that they actually do converge when you include the entire basis of linear functionals, there's an alternative way to solve to look for a solution directly. I won't explain the details of how this is done, but it's essentially kind of exercise in function analysis, but implement this numerically. And here's an example of C equals 8 and some external weight. The red curve with some wiggles down here, matched down to this, is the numerical solution we get by simply imposing crossing and that assumption that they're only scalar via stored primaries. And the blue over here is the Liouville spectral function computed from the DOZZ formula. And you see they nicely agree. There's some wiggles here that settle down as you improve the numerics. I should say that for this purpose, we didn't even need to assume unitarity. So that suggests that even without any other assumption, this is only solution to crossing. Just to demonstrate the numerical convergence is actually pretty non-trivial. So sometimes, depending on the value of the parameters, you start with some solution that wildly oscillating, but they eventually settle down as you improve the numerics by including more basis functions. Okay. Now, let me say a few words about superconformal theories. So we also like to use this kind of method to constrain some properties, let's say, of non-BPS operators in some known superconformal field theories that we'd like to understand better. So for example, in 2D, 2,2 superconformal theories, they are nice in that they often come in conformal manifolds. And there's an entire family of them. And that's because for 2,2 superconformal theories, marginality implies exact marginality. If you have a marginal operator, you can use it to deform to a continuous family of conformal field theories. And they provide abundant examples of interacting compact and generically irrational conformal field theories along the conformal manifold. So here's a cartoon of the conformal manifold. There might be some rational points, and sometimes there's some singular point where the spectrum becomes degenerate. So they become continuous near that point. And there's typically, when this happens, there's a sector of the theory that can be described by a non-compact CFT as opposed to a compact one. The Bootstrap method allows us to get a handle on the non-BPS operator content in these superconformal theories by, for example, by analyzing the OPE content of a pair of BPS operators. We can get some bounds, not yet solving the theory entirely, but at least get some kind of non-trivial bounds. So to do this, we need to figure out how to feed in the information of the moduli dependence. That can be fed into the OPE through some known Caroline relations or some protected BPS correlators. For example, if you take the superconformal nonlinear sigma model on K3 target space, it turns out that one can determine a certain, so in this case, the Caroline ring is trivial, but you can determine very non-trivially, rather, a particular integral of the BPS 4-point function in the cross ratio. And that's given by some formula. I won't have the time to explain this in detail, but this was actually motivated by heterotic type 2 duality and was established by some non-normalization results from the point of view of a space-time kind of string effective action, but for commodification on K3. But let me not go through that. Just to show an example of something that you can determine, and now you can feed this information into the crossing equation analysis of this 4-point function. So you know something about this integral, you can put some constraints. And you need to know about the superconformal blocks. It turns out we also know these n equals 2 superconformal blocks when the external operators are BPS. The internal operator can be BPS or non-BPS. So this we found these, how to compute these things in a convenient way by studying the n equals 2 cigar theory. But again, I'm not going to go through the details of that. I just want to show you some examples of the type of things you can deduce. These are still very limited information, but nonetheless, they're non-trivial. So here's an example for the K3 CFT. So the horizontal axis is this integral of the BPS 4-point function for a specific BPS operator. And you can put a bound on the gap of non-BPS operator in the OPE. So here it's 0 when this value is less than 0, and it's non-zero over here. OK, so there are many interesting physical interpretation of this picture, but I just want to point out one feature of it, which is that it asymptotes to this gap actually asymptotes to a quarter numerically. And that turned out to be saturated by this OPE in the A1 cigar CFT, which is a limit of the K3 when the K3 develops A1 singularity. Now, just to clarify, in the realm of classical hyperkähler geometry, if you develop a A1 singularity, locally that just looks like a Z2 orbifold. But in the CFT language, you have to be, there's more to it. you can turn a flat B field on the sphere that shrinks to 0 size in the orbital limit, and depending on the B field you turn on, the CFT may or may not be singular. For a specific value of B field, you have a singular CFT. For another value of B field, you have the ordinary orbital CFT, which is perfectly non-singular. This I'm referring to the singular CFT. Okay, so this is one example where this bound is saturated by known theory. Another example is that we can use it to explore possible 2,2 superconformal field theories with marginal deformation. What we do is that we take a pair of marginal chiral and anti-chiral primaries that deforms along the conformal manifold. We study their OPE. And here's an example. So for various no charge, you can try to bound the gap of a non-BPS operator in the OPE of a pair of chiral and anti-chiral primaries, and you get some bounds. It turns out that for some special values of some charge, again, these are saturated by some known theories, which are Lennard-Ginsburg models. By the way, I should say that in this case, I'm not assuming spectral flow symmetry. So, of course, for Calabi-Yau models, you have spectral flow symmetry, in which that was important in the work of Keller and Uguri in trying to bound the spectrum using the partition function. For us here, for the OP analysis, we don't actually know how to use the spectral flow symmetry in a useful way. But without spectral flow symmetry, you get this kind of, you get some non-trivial results already. Okay. Now, the last thing I want to discuss is to combine the two things I discussed, OP crossing and modulating variance. So now you can do it directly. You have both our constraints on the spectrum theory and the structure constants, but it turns out technically it's very hard to do these simultaneously on the computer. It's just because you have a lot of external primaries involved. It's a semi-definite programming problem that's very hard to solve directly. But in fact, that's also kind of too much information because you have all these structure constants floating around. You're trying to constrain some data in some huge dimensional space. It's not even clear what are the right questions to ask. I would like to know something about distribution of these OP coefficients and so forth. And a way to do this is to consider the partition function of higher genus Riemann surface. So the higher genus modulating variance does not give independent information from the sphere crossing and the torus one-point function modulating variance, but provides a convenient way to combine them. So here we can just consider partition functions, say at genus 2, and look at the conformal block decomposition in different ways. So we'll focus on genus 2 case. Just a partition function. So this knows about both the operator spectrum and the structure constants. Okay, that's what I said. Now, a few technical obstacles you have to get out of the way. Firstly, there's a conformal anomaly that you have to worry about. Depending on the choice of conformal frame, this partition function may not be manifestly modulating variance. You have to be careful with the conformal anomaly. For example, one way to form the genus 2 surface to parameterize it explicitly is by the plumbing construction. You can glue together using SL2 maps of a pair of two-hole disks to form a genus 2 surface. There's a way to write down the conformal block in this particular conformal frame, but it's not manifestly modulating variant, the result. There's another frame I call the Rainey frame, which I'll describe in a second, that makes at least a particular non-trivial element of the genus 2 modular group manifest. Okay. And we need some efficient method for computing genus 2 conformal block, just like the sphere 4-point Irrational conformal block, which was due to Zamolodchikov, the recursion relation. So that can be done. And we need a way to handle the semi-definite programming problem now with the many weights involved. This we haven't quite figured out how to do. Okay, but let me tell you some of the results. So, okay. First, let me say a few words about the recursion relation that allows for efficient computation of general higher genus Irrational conformal blocks. So it turns out that in the plumbing frame, there's a particular conformal frame in which the conformal block is such that its large C limit is finite. This unambiguously fixes the conformal anomaly because conformal anomaly takes the form of exponential of C times some function. So this recursion relation in the following form. It's a bit complicated, so let me just explain the various pieces of ingredients roughly. The conformal block depends on generally external weights. In this case, they're absent. There's some internal weights, and then there are plumbing parameters Qi, which parameters the moduli of the Riemann surface. The recursion relation is a relation that relates this conformal block to another conformal block of the same type, but with shifted weights. It may look like some kind of a mess, which it is, but you can put this on a computer and just produce a Q expansion using this kind of recursion relation. So let me say a few words about different pieces of ingredients. There's a part of this that's the global SL2 block. This is straightforward to calculate. And then there's a non-trivial C equals infinity semi-classical or classical limit of the vacuum conformal block. It turns out that the general expression for this, in principle, was obtained by a holographic dual computation, surprisingly. At the time, we weren't really thinking about this, but it turns out that the results in the paper with Simone Giambi and Alex Maloney applies to this. And then there are these recursion pieces that are related to shifted blocks with some coefficients that introduce poles in the center of charge. So I should say that the logic of this derivation, which I'm not reviewing, is you consider the analytic continuation of the conformal block in the center of charge to the complex plane, and you look at the poles and behavior C at infinity. So that's the philosophy. And these coefficients are all known. I'm not writing them explicitly. So this was originally due to Zamolodchikov in 1984, and for the hydrogenous case was generalized recently. Okay, and that was the recursion. I just want to mention that this allows now some efficient computation of a torus correlator or high genus correlator in principle in, say, Liouville CFT. And for example, can compute genus 1 two-point function Liouville theory and integrate in the moduli to get the genus 1 scattering amplitude in C equals 1 string theory by studying different OP channels and put them together. The result nicely agrees with the prediction of matrix model, which was solved by Greg Moore and collaborators in the early 90s. And they basically agree within a reasonable numerical error of like 1 or 2%. Okay. Now, let me say a few words about the Rayleigh surface, the Rayleigh frame. So we can describe a special Z3 invariant genus Riemann surface as a threefold cover of the sphere with 4 branch points, Z3 branch points. And so from the point of view of CFT, think of 3 copies of CFT on the sphere with 4 twist fields inserted. So that correlator is the same as genus 2 partition function in a special conformal frame. That corresponds to a special moduli, which is a one-dimensional locus in a 3-dimensional complex dimensional moduli space with this period matrix. The parameter Z here is just the cross ratio of the 4 points. Writing it in this way, the genus 2 partition function takes almost identical form as a sphere 4-point function. The only difference is the conformal block. The conformal block here is still secretly the genus 2 block, not the sphere 4-point Virasoro block, but we can compute it. And the crossing relation is the same. It's considered this OPE versus that OPE. This color represents different sheets, so these cycles go between different sheets, as you can label by the colors. Okay, so this corresponds to a particular involution that's a non-trivial element of the SP4Z modular group of genus 2 Riemann surface that impose some non-trivial constraints. And so you can decompose this genus 2 partition function written in this frame in this way. So it involves the sum of structure constant squared, now ranging over all the primaries in the CFT with some genus 2 conformal block that you can calculate. So I'm kind of running out of time, so I'm going to just show you that the various pieces of conformal block can be calculated. There's some explicit formula that you can find in our paper as an expansion, but numerically this is good enough. In fact, it turns out the expansion in the cross ratio, again, is not very efficient, but if you map to the elliptic gnome, it gives very nice convergence property. And this piece has some expansion which you can produce. The actual formula that we can use is much longer. I cannot even write as they are in Mathematica. This, if you look at our paper, you will take the PDF file and you zoom in 5 times, you might be able to read the formula. In very small fonts, otherwise there'll be no way to fit. Okay. Now, that was for the Z3 invariant surface. You can do this. If you go beyond the Z3 invariant surface, that sounds very complicated because the geometry becomes very, very complicated. It might be hard to calculate and how to take care of the conformal anomaly. But there's a trick we can do that allows us to formulate the crossing equation without having to explicitly form the geometry, because we can deform the geometry by equivalently inserting stress energy tensors on the different sheets. That corresponds to expanding the crossing equation around a more general geometry, away from the crossing invariant point in the more general direction in the moduli space. So the general crossing equation takes this form involving some OP coefficients and some generalized or modified conformal blocks. I won't say this in detail. Okay, so one can obtain some non-trivial constraints just by looking at some small pieces of this equation. So for example, one can find some kind of critical domain in the space of coupling, structure constants. So this is a plot in the space of 3 conformal dimensions. That is to say, what this plot means is that from the crossing equation, you can derive some constraints among the structure constants of large weights and small weights. So structure constants that depend on a triple of dimensions outside this domain are bounded by those that sit inside the domain. So there's some constraints that follow from unitarity and genus 2 modular invariance, which cannot be easily obtained by looking at sphere crossing alone, but it's easy to obtain from analyzing genus 2 modular invariance. But I should say that a systematic investigation of this is yet to be performed because it was difficult to implement the systematic semi-definite programming for this genus 2 crossing equation so far. Okay, so let me summarize. The gist I want to convey is that actually, despite a huge amount of knowledge that has been accumulated about 2D CFTs, we still know very little about the generic 2D CFT, which are, you might assume to be compact, unitary, with no actual conserved symmetry, with no actual enhancement of symmetry beyond Virasoro, and almost no such example. And our knowledge is embarrassingly little when it comes to trying to apply this to holography, because there's the impression that if you have a quantum gravity in ADS3, you're all set. It's still the 2D CFT, and we know a lot about 2D CFTs, but actually not so much. Not nearly enough to address interesting questions we'd like to understand from the holographic perspective. That's something we'd like to understand. But at least the axioms are clear, and we have some method to address them, maybe not very efficient at the moment, and lots of work to do. Thank you.